How we doing, guys? We're looking at maximum and minimum problems. If you're looking at text and test 5, it's page 121. We're looking at questions 4 and question 7. Question 4 asks us, in the given right angle triangle, ABC, the lengths of AB and BC vary such that their sum is always 8. If AB equals x, express BC in terms of x. Okay, well, hopefully that's manageable enough. This and this together have to be 8. So this is 8 minus x. If that was 3, this would be 5, for example. Okay, so BC equals 8 minus x centimeters, I suppose. Yeah, centimeters, you can see there is the unit. Find the maximum area of the triangle ABC. Okay, so find the maximum area. The first thing we need is an expression for the area, or an area function. Well, we know that area of a triangle is half the base times perpendicular height. So that's a half of 8 minus x times the perpendicular height of x. So our area function looks like this: 8x minus x squared over 2, which is a quadratic function. It's got a minus x squared. So it's an n-shaped quadratic. It only has a local maximum. That's what we're going to try and find, the maximum area that we can get. Okay, so here's our area function plotted out on GeoGebra, and you can see here at x equals 4, we seem to get our maximum point. Our maximum area seems to be 8 centimeters cubed when that distance is 4. Well, let's see how we work that out on paper. We have our area function a of x. Okay, or let's call it y. Okay, and what we want is, where is its maximum point? Well, our condition for that is that dy dx has to equal 0. Okay, so we let dy dx equal 0. What dy dx here? It's going to be 8 minus 2x over 2, or 4 minus x. You let that equal 0, you get 4 equals x. Okay, and that's what we saw in our graph, that our maximum point here occurs. 4, 8 was our maximum point on GeoGebra. Well, that's great, but that doesn't tell us the maximum area, which is what we were asked for. That tells us that we want this to be 4, and then this to be 8 minus 4 is 4 as well. Maximum area then is A evaluated at 4. So that's 8 times 4 minus 4 squared over 2. And that's going to give us 8 times 4 is 32. Take away 16 is 16 divided by 2 is 8 centimeters squared. So all of these questions are going to ask you to come up with some kind of function, then maximize or minimize that function by saying dy dx equals 0, and then come back and find the maximum value of that function. In this case, it was an area question. So question 7 is actually an area question as well. A closed rectangular box with a square base of side x and height h has a total surface area of 54. Express h in terms of x. Okay, so here's our rectangular box, height h, square base, which means both these distances are x, and it has a surface area of 54 centimeters squared. So to express the height in terms of x, which is what they've asked us to do in part 1, we're going to find an expression for the surface area. Well, this bottom square has an area of x squared, x by x, as does this top square. So that's 2x squared plus this side rectangle of x by h is the area of the rectangle, base by width. And we've got 1, 2, 3, 4 identical rectangles. So there's our area expression, and that's equal to 54 centimeters squared. So an expression for h, well, you're going to move that 2x squared over. You're going to say 4xh is 54 minus 2x squared, and the height can be given as 54 minus 2x squared over 4x. So there's an expression for the height of our rectangle. Part 2 then asks us to express the volume of the box in terms of x. Well, volume is length by width by height. That's x by h. x squared h. And now with our new expression for h, it's x squared times 54 minus 2x squared over 4x. So that's the volume given as a function of x. We've got x's that can cancel here, and if I multiply that out, I'm going to get 54x minus 2x cubed divided by 4, which can also be written as 13.5x minus 0.5x cubed. Part 3 then asks us for what value of x is the volume at a maximum, and hence find this volume. Okay, well, here's our function, minus 13.5x minus 0.5x cubed. So this is a volume function now, okay? And as x gets bigger and bigger and bigger here for values, it's only valid for values of x between 0 and about 5.25 there. As x gets bigger and bigger and bigger, the volume gets bigger up until 3. 3, you reach a maximum volume, and then for any value of x you go bigger than that, the volume of the box overall actually gets smaller. So we're going to find that the maximum value occurs when x is 3, and that is a maximum value of, it looks like maybe 27 there. But how do we do that? To find any maximum, you let the derivative equal 0, so v prime of x is going to be 13.5 minus 1.5x squared when you differentiate this, and we need to let that equal 0. So that means 13.5 equals 1.5x squared, and x squared is 13.5 divided by 1.5, which is 9, and x is 3. Now, or minus 3, if you go back to GeoGebra there, you can see that we had a minimum point at minus 3 as well. So we have 2 turning points we've discovered here at 3 and at minus 3. However, we're only interested in the one at 3. How do I find then the volume when x equals 3? Well, that means plug 3 back into this function here, and 13.5x minus 0.5x cubed. Okay, I'll do this down here, even though I really shouldn't. V of 3, I'm squeezing it in, which is what I give out to you guys for doing all the time, minus 0.5 times 3 cubed, which you can see on the calculator here gives 27. Okay, so that is our maximum volume is 27 centimeters cubed for this box, given the constraint that the surface area has to be 54 centimeters cubed and the base has to be a box. Okay, you might go now and do page 121 there, question 3, please. Thank you very much. I'll see you in class tomorrow.